All right, so the next speaker is Suman Kundu, and he'll tell us about the string theory for 2D MLs.
Thank you. So this work I am doing with Ofer and Tal from Weizmann. So first I will start with reviewing a bit about the 2D young mills, the older results. This is the action, and this theory is 2D. This is in any two-dimensional manifold, and it is exactly solvable. This is the exact answer, and it's sum over various representations. And dr is the dimension of the representation, and C2 is the second Casimir. And for a specific gauge group SUN, we let's assume this Tuft coupling. And in 93, Gross and Taylor did the large n expansion of this previous answer. And this is the big expression. But I won't explain all the numbers, but two things to remember is this exponential of area term and the area polynomials, and everything else is numerical numbers. And now you can see here various integers n bar, s and t and k. N bar in string theory, they interpreted it as number of oriented surfaces and number of anti-oriented surfaces. And that means the wall set is wrapping the target space n plus n bar times with S number of branch points, T number of tubes. Tubes can have three types of tube. You have orientation preserving tube, which connects the surfaces of same orientation, and orientation reversing tube connects the opposite orientation, and collapse handle connects the same surface. You also have various other fixed moduli. It's a very special kind of moduli, which are called omega points, and this doesn't give you the area contribution. So the claim is that n, or this 1 by n expansion result should be represented by a string theory, and the position of these branch points and the tubes and the handles are the moduli of this one set mapping, and integrating over each moduli will give you a lambda factor. Lambda will come from the coupling constant, and the coefficient perfectly matches with the symmetry factors of each moduli. Now in the string theory, the string tension would be lambda by 2, lambda is the Tuft coupling, and GS is 1 by n. Now, the full pure Young-Mills partition function in strict large n limit decouples into two parts, chiral and antichiral. But if you go further in 1 by n in couple of orders, you will see some interaction term, that is n bar type of interaction terms. So you can look at any simplified or special sector into for this pure Young-Mills. So you can only look at you can choose to look at the chiral sector or the full pure Young-Mills, or in the lambda is equal to 0 limit, which is a topological BF theory, or non-zero lambda limit. Now in each sectors, people have tried for a long time. The main characteristic difference between this column and this column is in the chiral sector, the wall sheet mappings have to be holomorphic maps. But here only holomorphic map will not work because it has chiral and antichiral both. And one such tries proposal was due to Horava from 94, and he used harmonic maps instead of holomorphic maps. So that has both the holomorphic and the anti-holomorphic together. Now in lambda not equal to 0, there is no example yet except one naive proposal by Horava again. To review a bit of Horava's theory, this is a harmonic topological sigma model. The action is this. In superspace formalism, it has two bosonic field X and B and two fermionic fields psi and psi bar. And this is the induced metric, and the action looks like all Nambu-Goto action, but it's not quite. And you also have this S1 interaction term. Now, this action is a Q-exact action, and you can use localization. Okay, and you effectively taking t to infinity, and also you can show that one loop determinants around this classical solution will cancel between the bosonic contribution and the fermionic contribution, and and the non-zero modes cancels out, but the zero modes will stay, and the integration over those zero modes will reproduce the expansion coefficient in the large n expansion. Now about the S1 term, this is the proposal in the Horaba's paper that he used this action with a pi mu. Pi mu is the projector orthogonal to the world sheet. In higher dimension, it is well defined, but in 2D, it is identically zero because it has finite value on folds or any moduli. We used a bit different action. I will explain. And another issue with this case is in d is equal to 2. In d is equal to 2, the configuration space and the action are both singular, and the action is non-vanishing just on the folds, and the action is non-vanishing just on the folds, and the one loop determinant, like it is very hard to calculate one loop determinant around these solutions. So instead of this Nambu-Kudo type formalism, it would be better if we have some Polyakov type calculation. Now this is the equivalent Polyakov action. Now this capital HAB is an auxiliary metric instead of induced metric, and accordingly we gauge fixed to conformal gauge, and due to that we need ghost fields. Note this HAB is function of theta and theta bar also, and that's why there are total 4 components, and same as for the ghost fields. Since these ghost fields have total 4 contributions, 2 from the bosonic, 2 from the fermionic, they also cancels exactly, and this doesn't have any extra non-trivial zero modes. So the action is very simple, and now let's say the equation of motion for this action, the equation of motion is this. Generically, the solution looks like this, where it is function of J and Z bar both, since it is not holomorphic or anti-holomorphic, and also can depend on AI parameters. Now we have to integrate over all these AI parameters. And but for generic, so now the claim is that for generic AIs, this solution will not satisfy the Virasoro constant, that is the stress tensor won't be 0. But once you do the AI integral, and you will see that there are saddle points, and on the saddle points, this will satisfy the Virasoro constants. So finally, the formal solution looks like this, that it's an integral over AI, and the action is calculated on cell. And this is just a plus minus 1 coming from the one loop determinant, since they cancel, leaving minus plus minus side. Now as the S1 action, instead of the pi mu, we used k mu, and pi mu was identically 0, but k mu is the extrinsic curvature on the wall sheet. So that captures a delta function contribution from each moduli, like tubes or the branch points, and using this action, it matches with the topological Yang-Mills answer. So now, after this closed string case, let's look at some Wilson loop expectation values also. And again in 93, Gross and Taylor did the large N expansion of these answers. These are all well-known answer, and interpreted it as if it is coming from some string theory. So I would like to mention that other than these usual Wilson loops, there is something called figure 8, which has holomorphic mapping in one side and anti-holomorphic mapping in other side. This is called twist point, and this was one of the special cases, one of the new features in this Wilson loop case. So for the we use the same theory but with fixed boundary, and the action remains same. All we have to introduce is the boundary condition. Boundary condition effectively keeps the position of the boundary fixed, because we are looking at Wilson loop. And now to deal with this figure 8, it was very necessary to have a mapping of the form of some holomorphic function plus anti-holomorphic function. Okay, which was now previously I told you this kind of solutions doesn't satisfy the Virasoro constant if we use the conformal gauge. Now we had to change the gauge. What we did is we set this auxiliary metric HAB to the classical induced metric itself. And with this gauge we showed that the gamma 8 contributions comes out correctly, and it satisfies all the equations like equation of motion, boundary condition, and the Virasoro constant. Now, after this open string example, we also try to look at the finite lambda case, where other than these two terms, we have also added, we had to add two extra accent term, which the first term calculates the area, and the second term gives you the area polynomial, as I told you previously. Now, for finite lambda, due to these terms, localization doesn't work. But we can use, we can take t goes to infinity limit by hand, and we can localize to harmonic maps as it was prescribed. The new moduli are branch point. The new moduli are branch point and the collapsed handles. And using this action, we this is a proposal. We didn't finish the calculation. It's an ongoing work, and we hope to get the result from this. This is the conclusion. These are the things we tried, and we in the near future we want to finish this finite Luft coupling case, and the future goal is to add the dynamical boundaries or to look at the higher dimensional effect of this string theory. Yeah, thank you.
Questions? Yes.
What is the perturbation on the world sheet that's equal to trace of b squared if you're doing perturbation theory on BF?
Trace of b square, you said?
Yeah, and to work around the zero coupling limit?
Yeah.
Or is that what you're doing to go to non-zero coupling?
Yeah, so in the so you have this, so the h square can be written as bf plus b square and lambda times b square, and you set b lambda to 0, and it's just a bf theory. So that was the previous case. Now here, I guess the lambda proportional to lambda terms would be the equivalent of this b square. So here, these two terms has this lambda coefficient in front, and presumably this will be the dual.
Thank you.
Other questions? Okay.
Okay.
Thank the speaker.